that are incompatible with the absoluteness of measurement. So let us welcome Dr. Saha, and let's listen to him. The stage is all to you now. Thank you.
Yeah. Thanks for this nice introduction. Am I audible, right?
Yeah, you are audible.
And can you see the screen?
Yeah.
Okay. Okay. Okay, yeah. So thanks for this nice introduction. And let me also thank the organizer of this event. Yeah, so as for inviting me to give a talk. So actually, I had two topics in my mind to talk about today. So one is like the link between quantum contextuality and quantum advantage in communication, and the other is the topic that I'll be presenting. And I was not certain which one choose, but I noticed that Professor Archon Mojumdar has covered the other work in his talk on 10th of May. And secondly, the thing that I'll be presenting today has surprised me the most in quantum mechanics so far. So I thought it would be good to share this with you. Particularly, there are lots of young researchers and students are in the audience. Okay, so and I would expect lots of questions and discussions. And let's see how it goes. So let me start with the postulates of quantum mechanics. Yeah. So any preparation of quantum systems is described by a vector that belongs to some Hilbert space. So here I choose to be in the ideal case and isolated systems. Okay. And any measurement that we can perform on this system basically is described by a set of projectors. And if we observe d different outcomes of this measurement, there are d different projectors such that they sum up to identity. And so if I prepare a quantum state psi, and if I measure this particular measurement, then I can I can do this many times, and then I can get the probability of different outcomes A. So right, and that probability is given by the Bond rule. So you take that projector, the respective projector for the outcome A, and then you take the inner product with psi. And if I get outcome A, then the state collapses to this particular state according to the collapse dynamics. And then the time evolution of the quantum states is given by, it's described by unitary operation. So the state of a later time is connected by the unitary transformation. And then if we have a composite system that is made of two subsystems, let's say A and B, then the state of the composite system belongs to the tensor product of the Hilbert spaces of their component systems. And again, like you can think of, you can perform some doing measurements on their subsystems, and you can get the probabilities of the measurement outcomes by this. Okay. So there's one thing that I want to mention is that I refer to here the operational quantum theory. That means that it prescribes mathematical objects to experimental procedures and predict the empirical probabilities that we observe in the experiment. So here we do not talk about the actual physical system, such as like psi is the realist state of the physical system and so on. So forth. Okay, so this is the minimalistic approach. We want to just predict the empirical probabilities of our experiment. Okay, and The next is when you say quantum theory, we usually mean that the quantum theory is valid for any physical system. So the quantum theory is applicable to all physical systems, including the macroscopic system, right? So it might be very difficult to describe a macroscopic system using quantum theory, but in principle, it can be done. Okay. And the next is, as you can see, that there are two different dynamics in quantum theory. One is the time evolution, this dynamics, and the another is the post-measurement dynamics. So after the measurement outcome, the state collapses some other state. And the issue is that quantum theory doesn't specify the exact boundary of the applicability between these two dynamics. Okay. And this is actually a basis for various issues in quantum mechanics, like measurement problem. Okay. So, well, I mean, the measurement problem is a problem for orthodox interpretations of quantum mechanics, where where the quantum state is taken to be the realist description of the physical system. But I mean, this is basically the basis of various issues in quantum mechanics. So let us first point out that this tension between the two dynamics in quantum theory may lead to some inconsistency at the empirical level, at the level of observed probability. And for that, we have to consider a famous thought experiment proposed by Wigner. Okay. So what happens here? So here is an observer named as friend, and she's performing a measurement on a quantum system. Let's take that system to be a two-dimensional quantum system, the qubit. Okay, and let's say that she's performing sigma z measurement on that system. Okay, and this is a lab in which she is performing this measurement, and this is an isolated lab, and this doesn't interact with the environment. Okay. Now Wigner and his student, okay, describe the combined system of the quantum state and the isolated lab using quantum theory. Okay. They are describing the interaction between these two systems using quantum theory. Now see, friend is a macroscopic object. My friend, including this measurement apparatus and everything inside the lab, the huge macroscopic system, right? So which might be very, very complicated to describe by quantum theory, but in principle, it can be done. I mean, in principle, all these macroscopic systems are made of subatomic particles, and in principle, one can it has a quantum mechanical descriptions. Okay, so let's take that F is basically the initial state of the isolated lab. Okay, so isolated lab means the friend, the measurement device, and the environment. So everything which is isolated. Okay, yeah. So this is the initial state just before the measurement is performed on the quantum space. And let's take the F plus minus is basically the final state after the measurement is done. So F plus is basically the final state such that the measurement device shows a definite outcome +1, and the friend observes a definite outcome, okay, +1, and F minus is for the minus outcome. Okay. Yeah. So after the measurement is performed here, friend basically observes a definite outcome, and the measurement device also shows a definite outcome of the measurement. Okay, and yeah, so friend can also encode this information via ancillary system. Yeah, that she has obtained a definite outcome. Okay, so she doesn't reveal the outcome, but she can just encode this information. She has obtained a definite outcome. via qubit, and she can place that qubit just outside the lab. Okay, and any observer, such as Wigner or student, so we call such observer as super observer because they are observing another observer. So any super observer will be able to know that, okay, friend has obtained the measurement out, right? Now, yeah. So now, so they are basically describing the whole process via quantum mechanics. Okay, that the physical interaction between the qubit and this lab, including, let's say, friend, is certainly a measurement process according to friend, because he has observed a definite outcome. It has to be a measurement process. Okay, but quantum theory doesn't specify whether this interaction should be described by the time evolution or the post measurement dynamics with respect to a super observer. Because yeah, so anything that they applies seems consistent, seems correct according to the four postulates of quantum theory. So for example, according to Wigner, let's say the combined system evolves via unitary. This is just an interaction between two systems. So this basically, I mean, this can be described by a unitary operation. Okay. So, and yeah, so, but this unitary should satisfy certain conditions. And that comes from the empirical facts. So for example, if the state of the qubit is 0, okay, then after the measurement is performed, the state of the qubit remains 0, and the state of the friend and the lab should be F plus, and that is certain. Okay, because this happens. This is an empirical fact. So this unitary, according to the Wigner, whatever be the unitary, it should satisfy this condition. So similarly, if the state of the quantum system is 1, and this is the initial state, and the final state we know it has to be like this, so this unitary also should satisfy this condition. Now, if the state is a superposition of 0 and 1, the unitary, if we apply the unitary, then we get this entangled state. Okay, so if the state is superposition state, according to the Wigner, the state after the measurement is done should be like this. Okay, whereas his student, he wants to describe this interaction via the post measurement dynamics, because he thinks that, okay, there is an observer, he observes an outcome, so it has to be described by post measurement dynamics. So according to him, so the initial state, if the qubit state is 0 at the F state, this is the initial state. At the end of the measurement, it collapses to this state. If this is the initial state, 1 and F, at the end of the day, it should collapse to this state. And if this is the state, is a superposition, then it should collapse to a mixed, it should collapse to either this state or the other, depending on the outcome. So it should be a mixture of these two states, according to the student, because it collapses to either this state or that state. And since the superobserver doesn't know the outcome of the measurement, so it's a mixed state. Okay, good. Now, as you can see that student and Wigner, they assign two different states to that combined system. And then if any super observer measures this particular measurement, okay, where F is basically the entangled state, this is the entangled state, then according to Wigner, the first outcome is certain, because this is basically the projector corresponds to this state, right? However, according to the student, this is the state, so he anticipates both the outcomes are equally likely, right? So as you can see that they actually expect like different empirical probabilities for the same systems. Okay, and they if the same measurement is performed. Okay. So such an inconsistency is not expected in any physical theory, right? Like, so I mean, uh, any physical theory, the empirical probability should be unique, should not depend on the perspective of an observer. I mean, that is what is expected. So yeah, so let us now try to formalize the two perspectives of these two super observers, Wigner and Friend, and his student. So such that like they are consistent on their own. Okay. So according to student, any measurement that is performed by some observer yields a single outcome, and that measurement is an absolute event irrespective of other observers and processes. So it means that if a measurement is performed, someone observes an definite measurement outcome, that means it should be considered as a measurement for any observer. Okay, so measurement is basically an absolute event. It's not a subjective, it's an objective. Okay, that is what it means. And that's why this should be the correct description of the combined system. I mean, any super observer should apply the post-measurement dynamic. On the contrary, Wigner thinks basically the negation of this. Okay, so that we call, let's say, the non-absoluteness of measurement. That is, the measurement is not an absolute event with respect to an observer unless that particular observer observes an outcome. So unless that observer observes a particular observer observes the outcome, it's not a measurement process. I mean, so it's still, so here Wigner, any super observer should invoke the unitary dynamics to describe the physical system, so to describe the combined system. Okay. Now if you, yeah, so basically these two are two different perspectives, right? So now if you take quantum theory along with absolute of measurement, this is consistent because this should be the correct state. And if you take quantum theory along with the non-absolute of measurement, this is also consistent. This should be the correct state. Okay. Yeah. Okay. Yes. Now, yeah. So let me just mention one thing, that such a discrepancy
Excuse me.
Yeah. Yes.
So, sorry to interrupt. Can you please just reiterate, like, what is this absoluteness of movement? Like, I could not get the absolute event irrespective of other observables and processes. That part.
Yeah. Sure. So here, since friend measures the friends observes a definite outcome. Okay. So this is a measurement process according to the friend, because she observes a definite outcome. So now absolute of measurement says that it is an objective fact, and measurement, so every other observer should treat this now as a measurement event, and they should apply the post measurement dynamics in order to describe this. Okay, so if somebody observes something, okay, that measurement is an absolute event whether there are some other observer is present or not. Okay, this is what means the absolute.
Got it. Thank you.
And the non-absoluteness is basically the negation of that. So it's like the Wigner is saying that, okay, I haven't seen any outcome. Yeah, the friend is saying that he has obtained a definite outcomes, but as long as the observer doesn't see an outcome, it's not a measurement event. Okay, it should be described by the unitary process. Okay. Yeah, so just let me just point it out that in classical theory, there is no discrepancy like this, because there is a unique dynamics, and if you apply that dynamics correctly, you will always get a unique state. So there is no issue with this. Okay. So now the question that we address here is this: that is it possible to operationally test quantum theory with AOM and quantum theory with NOM without invoking the details of the experiment? Like if you don't know the quantum states which is coming in the Wigner's first experiment, and the measurement is performed by, let's say, friend and all the details, can we just repeat, or can you just say something about which is correct or which is wrong? Or in other words, that these two things, like quantum theory with AOM and quantum theory with NOM, gives rise to two sets of probabilities, like observed probabilities, that can come from any quantum states and measurements. So like if you can consider like any quantum states and any quantum measurements, so they should give you a set of probabilities if you invoke AOM, and they should give you another set of probabilities if you impose NOM. Now, can we discriminate these two set of probabilities, or whether these two set of probabilities are the same? Okay, this is basically the question that we can address. Okay, so for that, we have to consider an extended version of this Wigner's friend experiment. So what happens here in this extended version is, yeah, so Alice, so now friend, the friend is basically the same thing, the same setup, but friend receives an input X. Okay, this is a classical variable, and that can take values like 0, 1, 2, 3, something like that. And also the super observer also receives an input that also takes values 0, 1, 2, 3, like this. Okay, so now friend state, knowing the value of X, is denoted by this f of X, because in her mind, in her brain, at some point the value of X is stored. So yeah, so this is, I denote that state to be f of X. So this happens at the first, they receive some input, classical inputs, and then our friend receives the quantum state outside, from outside the lab, that is psi, and then depending on this, the value of X, the friend makes a measurement, performs a measurement on the system, and that measurements is denoted by this. Okay, so here we take, like for simplicity, we take okay, there are two, this is a 2 outcome measurement, so this state is basically a qubit state, and this could be any rank 1 projective measurement. Okay, so depending on X, this measurement, the basis depends on the value of X. For different X, Alice basically choose different directions of friend choose different directions of her measurement. Good. Now, so after the measurement, she observes an outcome, right? And let us denote that outcome by A bar. Okay. So, and let's say the friend state, knowing the value of X and the outcome A bar, is basically this. Okay. So this is basically the friend state of the state of the whole lab, which says that they observe the outcome A bar, given that they have obtained the input X. Okay. Now, here it is important to note that for a given X, f of A bar given X for different outcomes A bar must be orthogonal to each other, because these states are distinguishable, right? Because I mean, this corresponds to different outcomes, so these states must be distinguishable. That's why they are orthogonal. And similarly, this f of A bar given X for different X are also orthogonal, because they should be distinguishable as well. because they correspond to different values of X. Okay, so this should hold. Okay. Yeah. So in this case, this psi, okay, I can always express in terms of these basis vectors, okay, for a given X, and this will be some superposition in terms of this basis vector, and according to the NOM, the state after the measurement should be like this. It should be an entangled state. Okay, that yeah, it's a psi X given that the friend observes outcome 0 given X, and psi perpendicular given yeah, the friend observes outcome 1 given X. So I denote the outcome by 0 and 1. Okay, there are two possible outcomes, and this is the state according to the absolute of measurements. It's a mixed. And after that, our super observer measures certain observable on the combined system of the qubit and the lab, and that depends on the value of W. Okay, so the measurement by super observer on the combined system depends on the value of W, and let's say for example, for W is equal to 0, the measurement is defined by the set of projectors. Okay, so and it means that for each X, there are two different projectors. Okay, so this is one projector that acts on the combined system. This is another projector that acts on the combined system. And basically, the system, the qubit is measured in the same basis, like psi X and psi perpendicular, and the friend is measured in this basis, that whether she observes outcome 0 or 1. Okay, and so there are let's say n number of X's, so there are like 2n number of such projectors, and those projectors are orthogonal to each other. If you take any two projectors, they're orthogonal because these states, the friend states, are orthogonal to each other. Right? And so the Hilbert space that corresponds to the lab must be huge, right? Because it's a macroscopic system. So we should consider another outcome corresponds to the projector identity minus the sum over all these projectors, okay, to satisfy the completeness conditions. But the outcome of corresponds to this projector will not occur because the state is either this or this, and in either cases the state has 0 basically overlap, 0 support, has no support on this project. Okay, but for the completeness we have to like consider the other outcome. Yeah, so for example, if I take like X, so let's say there are two different values of X, like denoted by 0 and 1. So A0, which is basically the super observer's measurement for W is equal to 0, is basically this. Okay, so there are 4 projectors and they are orthogonal to each other because if you take any 2 of them, they are orthogonal to each other. Yeah. So now, yeah. So this is A0, and when W is not equal to 0, then the super observer measures like certain observables. That is also described by a set of projectors like this, and so these projectors. So there are basically for each A and X there is a projector, right? And these projectors actually belongs to this subspace. Okay. Okay. That means that it will never happen that Alice, like the friend observes some input X, and after the measurements of the super observer, she observes some other input X dash. So just to ensure this, the projectors should belongs to this subspace. It should not overlap with the subspace corresponding to different X. Okay. Yeah. So in summary, what is happening is this, that so in each run of the experiment, at T0, they receive some input X and W, and then a quantum state enters into this lab, and then at T2, friend measures an observable according to her input X, and after that, depending on W, the super observer applies the measurement and obtains the outcome A. Okay. So if you see that the measurement by the super observer reveals both the values, the values of A as well as the values of X. But so since X is given, I know the value of X. I mean, what would be the value of X? So that's why we can just ignore the outcome X, and we can consider the outcome A. Okay, because the outcome X is sort of fixed whenever this input is fixed. Okay, yes. So and this is how you can define the probability of observing an outcome A for a super observer. Okay, given the input X and W, right? So this is, yeah. So you can perform this experiment many times, and you can obtain this this set of probabilities for any quantum states and measurements that has this structure. So we do not assume what is the state and what is the measurements, but we assume that the measurements and the measurements has this structure. Okay. So basically, you now you can obtain a set of probabilities that can come from different that can come from different states, right, and measurements. If you impose AOM, and you can also obtain a set of probabilities from all possible quantum states and measurements of this form if you impose NOM. So now the first thing that you have shown is that this set of probabilities is a subset of this. Okay, and this holds for any scenario. So scenario means that the number of the variable X, W, and A is fixed. Okay, so this actually defines a scenario, that what are the number of inputs that they receives and the outcomes of the measurements. If you fix that, then the set of probabilities in AOM is a subset of A. And secondly, it's a strict subset of NOM. That means there exist some probabilities in the set of NOM, like quantum theory, along with if you impose NOM, that cannot be achieved with using quantum theory with the absolute of measurement. Okay, and the simplest example is this. So you can take that there is no X. Okay, I mean X is unique. Okay, so friend always measures certain observable. Okay, doesn't change, it's fixed. And there are two possible observables for the super observer, denoted by 0 and 1. And if you consider this quantity, so it says that if Wigner's variable is 0, like if W is 0, then yeah, so this is the probability that he observes 0 outcome, and this is the probability that he observes 1 outcome. And this is, if Wigner's input is 1, then this is the probability that he observes a 0 outcome. Now you can show that this quantity is bounded by half if you impose a AOM. Okay, and that holds for any quantum states and any quantum measurements. But if you consider NOM, then there exists quantum states and measurements such that this quantity can go up to 1. Okay, so yeah, so now so this is an example that this is a bigger set, and there exist probabilities that cannot be achieved by NOM. Now in classical theory also, you can actually go up to half. Okay, that you can show. Yeah. So if you explore more, then what you will find is that there is a hierarchy between the set of probabilities between classical quantum with AOM and quantum with NOM. Okay, so in this case, the classical and quantum with AOM is basically the same, but NOM is giving us the more. But there is a you can also discriminate all the three set of probabilities in the same experiment, and that experiment is also it's just little bit just introduce. You have to introduce X here and the bipartite system here. So what happens is this, that is basically the same thing, but instead of a single system, instead of one system is entering this this lab, this is a composite system of 2 qubits, let's say. So, and 1 qubit goes to Bob, and Bob measures also certain observables and obtains some output. And this remains the same. It's basically the same thing here. And you can also define probability in this experiment. Like, this is just, there is no Wigner in this case. So this is just a simple, like given Y, Bob measures certain observables and obtains some outcome B. But here, depending on X, Alice measures, like Alice or friend measures some observables, and then after that, super observer measures another observables, depending on that. And you will get the joint probability of A and B given X, Y, and W, right? You can obtain such probabilities in this setup. Now you can consider, yeah. So now basically we consider like X can take two different values, 0 and 1, and as well as W and Y also takes two different values, 0 and 1. Okay, so now you can define a linear combination of these probabilities, which is nothing but the Bell expression, the CHSH expression. Okay. So yeah, given that W is equals to 0. So this is basically this is basically the CHSH expression, given that Wigner's input is 0. So yeah, so this basically means that if X and Y are both 1, then they should be different. The outcome should be different, A and B. Otherwise, the outcome should be same. So that is what you want in this expression. And you can define another expression, the same CHSH expression, but with when the W is equals to 1. Okay. And let me just remind you that this expression, the CHSH expression, if you just do not assume, do not consider this this Wigner's friend and everything, just if you consider like the usual Bell setup, it can be maximum 1/4. Okay, it can go up to 1/4 in all classical theories and local realist theories. Okay, so but in quantum mechanics you can go up to this value, which is around 0.85. But here we are considering basically two CHSH expression for different inputs of W, 0 and 1. Now, yeah, so now you can prove that if you consider AOM, that is the absolute of measurement, this measurement is absolute, then the value of P1, the CHSH expression for W is equal to 1, is bounded by this expression. Okay, it cannot be, it is somewhat dependent on P0. Okay, and from this you can get this plot. Okay, so this is basically the plot of what are the values of P0 and P1 can take for different theories in different theories. Okay, so P0 and P1 both can go up to 3/4, that is 175 in classical theories. So the values that one can get in classical theory should be in this region. Okay, And according to this this observation, you can like see that the values in quantum theory with AOM should be inside this region, the region that is denoted by black line. Okay, and now you can show that there exist quantum states and measurements. Yeah, if we impose NOM, that can achieve this value, which is outside the set of AOM. Okay, so yeah, so this is the situation that you can find that quantum theory with NOM is a strict superset of quantum theories with AOM, which is also a strict a superset of classical or local realist theories. Okay, and from there you can also define an inequality like this, that yeah, this is a linear inequality, and this should be bounded by 3/4 in AOM. This inequality is something like this. Okay, and you can go up to 0.85 in AOM. So how much? So it's yeah. So don't have much time. So yeah, so I will skip this. Yeah, so before I go into the interpretations of quantum mechanics, let me just tell you a couple of comments. So first is that, so let us go back to this, the simplest scenario. Okay. So so firstly, this experiment is not completely impossible to realize at it may sound. So we consider like this, the friend, as an observer inside this lab, but all we need is a system that can register the outcome of the measurement. Yeah, and then we need a quantum control of that system. Okay, that is what we need. So I mean, in quantum field theory, or in even other theories, we talk about like Alice falling into black holes or quantum experiments near event horizon. But I think this experiment is much simpler one than that. And secondly, even if this is not an isolated system, even if this lab is very difficult to make it isolated because it's a macroscopic system, and even if we do not have a full control over this macroscopic system, this inequality is basically robust. Okay, so if you include all those non-idealities, okay, then this bound will go up, right? And we still have a room to see a violation. Okay, so this is a robust inequality that can be in principle tested in the lab, and then you can say that, okay, this quantum mechanics with AOM cannot be true. Okay, this viewpoint that measurement is an absolute fact, is an absolute event, it cannot be true. You can certify this. Of course, it depends on the outcome of the experiment. Yeah. Okay, so yeah, so let me just comment briefly on different interpretations of quantum mechanics with respect to what we have said. So there is a class of interpretations of quantum mechanics where the measurement is basically inherently is a process that is inherently classical, and this is and there is no ambiguity between the measurement and the time evolution. So basically, there are like two distinct dynamics, right? And such theories are like collapse theories or the ETH approach. Okay, and in those interpretations, measurement is basically an absolute event. So this is compatible with absolute measurement, and certainly this is not compatible with non-absolute measurement, and this is also consistent. There is no inconsistency. Okay, and so there is another class of interpretations like Bohmian and many world and relative state, where where measurement is like emergent phenomena. Okay, so this is not the actual thing. For example, in many world, all the outcomes occur in a measurement. Okay, so it's just an the entangled state remains. I mean, it remains in the entangled state. It's like the observer is in the different worlds respective to different outcomes. And this is the correct description here it should be described by the unitary matrix. So it is compatible with NOM, and it is also consistent. There is no inconsistency. And another category of the interpretations that we have is based on the idea of anti-realism. That is the fact that there is no objective reality. Okay, and we call those like Copenhagenist type interpretations. Okay, and so yeah, and so there so there we actually assume that quantum theory, operational quantum theory, is the correct one, and all the measurements yields a single outcome. Yeah, so there are actually two types of Copenhagenist type interpretation. So one is we call the objective Copenhagenist interpretation. That is more with the alignment of originals Bohr's idea. Okay, where we say that the measurement outcome is an objective fact of any observer. And there is another class of Copenhagenist type interpretation that is called, let's say, perspectival. For example, cubism, and for example, relational quantum mechanics and consistent histories. I think they fall into this category, where observing a measurement outcome is a subjective fact. Okay, now here in this in such interpretations, you must invoke a split, or sometimes it's called the Heisenberg cut. Okay, that actually represents the boundary up to which an observer describe the physical system using quantum theory, and after that he must invoke classical theory. Okay, that is basically the split. Okay, so I don't have to go into the details, but the split, you have to consider this idea of split in Copenhagen's interpretations. And you must, any agent who is describing physical system using quantum theory must put the split in front of him, because yes, and also the split should be, so here in the Wigner's friend, the split should be anywhere between just before him or after the measurement apparatus. Okay, so the super observer has this can put the split can be anywhere, and depending on that, the state, the combined state will be the mixed state or the entangled state. And in perspectival, this super observer has the complete freedom of choosing where the split should be. It's clear. Okay, so if he thinks that the split is here, that means it's compatible with AOM, and the split is outside the lab, that means it's compatible with NOM. So it's not compatible with any of them, because the super observer has this freedom, and it's not also operationally consistent, because it depends on where the observer, the agent, wants to put the split. But also it doesn't need in perspectival Copenhagenist type interpretation. We do not need consistency, because it's all about the agent and the rest of the world. Okay. However, in the objective Copenhagenist type interpretations, it's not clear that how it fits with this analysis. Yeah. So yeah. So with that, let me just finish with this remark that this work is done with a PhD student, Subayan Sarkar. He's now a postdoc in Belgium. Yeah, it's published recently, and these are a few references. If somebody is interested, may go through these references. The other references can be found in this paper as well. So I think, yeah, that's all I wanted to say. Yeah, thanks for your attention.
Yeah, thank you, Dr. Shah, for this very intriguing discussion and the lecture. The session is open now for the questions.
Yeah. So there's this.
Any question, please? So I have one small question. So is there any way, means any point you are taking into account the hidden variable theory here?
Yes, it's a good question. So the answer is no. So
Okay,
it's all about the operational quantum theory.
okay.
Okay, it's all about the operational quantum theory,
Mhm.
where we are minimalistic. We do not assume anything about the actual
Okay.
state or hidden variable.
Mhm. Okay. Any other question?
Can I ask a clarification question?
Yeah, please,
Yes, of
please.
course.
Thank you for your talk. Could you please explain the definition of operational quantum theory and without operational quantum theory?
Yeah, so in the operational quantum theory, you describe the processes. Okay. So for example, you describe a preparation process by a quantum state, you describe a measurement process and time evolutions, so on and so forth. You do not talk about the actual state of the systems. Okay. That is the operational approach. You do not know anything, you do not want to say anything about the actual physical state of the system. The goal of your theory is just to represent these different processes by mathematical objects and predict the outcome of the probabilities that you observe in the experiment. You do not want to say anything about the physical system more. Okay, that is what operational theory is.
Thank you.
On the contrary, you can think, so for example, the orthodox interpretations of quantum theory, if you consider that, it tells you that psi is actually the physical state of the system. Okay, and the measurement is actually described by a set of projectors and something like this. Okay, so there you say something more about the physical systems. That is, yeah, that is a realist approach to any physical theory.
So if I understood correctly, what is inside unitary operator, we don't want to say anything.
Exactly.
We know the properties.
These are just like a black box. For an operationalist, these are like a black box.
But they possess some certain properties, right? The unitarity, like which you have mentioned, time evolution.
Yes,
So,
exactly.
Yeah. Okay.
Yeah. So at the end of the day, you do some experiment and you observe probabilities of different outcomes. And it seems like if you follow this set of rules, if you follow this set of prescriptions, then you are almost accurate. Yeah, to predict the experimental observation. So
Okay.
any theory has this goal that it has to reproduce the probabilities that is observing the experiment.
So measurement which you are considering here, it is von Neumann measurement, right?
Yeah, exactly. So we consider here this is an isolated system, an ideal.
So, yeah. Okay. When we need to consider von Neumann and not von Neumann.
Yeah. So yeah. So you can think that there is a system and there is an environment here, and you can, so you perform a measurement, but that measurement involves an interaction between the system as well as the environment, and you can also derive the description of the measurement. Okay, that is the most general form of a quantum measurement. that is described by a POVM. Okay.
Mhm.
Yes, but this is basically the fundamental. This you take as a postulate and things. It
Okay.
correctly reproduce the probabilities, and from there you can further derive what would be the general form of the measurements.
Okay. So PA, this is matrices, right? These are the
Yes,
vectors.
these are projectors.
Yeah.
So
Okay.
yeah, so maybe one thing I should mention, that this definition is equivalent of saying that this measurement is described by a Hermitian operator,
Mhm.
because Hermitian operator has a spectral decomposition, and and those eigens projectors for different eigenvalues are basically this project. So this
So
is
PA are made of eigenvectors, right?
yes. So exactly. So PA are basically the like it's a projector that is psi, psi, a, psi, psi.
Thank you.
Just the outer product of the eigenstates.
Sir, you spoke about the exact there is a boundary between post measurement dynamics and unitary dynamics. So, uh, do we have a converging point for these two dynamics, or how do we choose these two dynamics? Does it depend on our the situation or something else?
Yes. So so this is the thing, that this set of postulate doesn't specify that which dynamics should be imposed always. Okay. And one such example is this Wigner's friend example. Okay. So here, friend is measuring certain observable on a qubit. Now, these two observer is described are describing the physical process. Now, the postulate has become silent, that whether a super observer must invoke the post measurement dynamics, or the super observer must invoke the unitary dynamics. This is a situation. It's not clear that which dynamics one should use to describe the interaction. Okay. So on one hand, you can think this is just an interaction between two quantum systems. So it should be described by a unitary, right? This is just an interaction. Whatever is happening inside the lab is basically interaction between this qubit and this lab. On the other hand, you can think from a different perspective. Okay, so there is an observer, and C observes a definite outcome. So it must be a measurement is not be described by a measurement process. And so there's a tension that which one I should apply here in such scenario. And the standard quantum mechanics, or the textbook quantum mechanics that we know, is it's not clear that it doesn't specify.
Okay. So it depends on the situation. There would be situations we would be using both. There would be situations we'd be using only unitary or post measurement.
Yes. So I mean, here I would say, so here Wigner is applying unitary, and the student is applying the post measurement dynamics. Okay. And they come up to different conclusions.
Okay, yeah. Okay, then thank you.
Yeah, so we don't know which one is correct. So this is if you ask me which one is correct, I don't know which one is correct. We have to go, we have to perform such experiment in order to know which one is the correct description.
Okay, nice.
Thank you, Dr. Saha, for all these clarifications and all with so much precise details. Any other questions? If not, then let's thank Dr. Debashis Saha for this wonderful talk, and we move to our next speaker, another Very exciting talk coming up. And our next speaker is Dr. Solomon Ivan, who is an associate professor at Indian Institute of IQ.